everything fine with you now?
الحين انتظر بشوفه.
Okay. But in general, the problem from your computer. Okay, check it, please. Okay, now we will discuss the same previous circuits in module 1, rectifier circuit, single phase and three phase, but rather than we use diode, we will use thyristor. So we will have a single phase rectifier circuit, but we will use controlled, which is thyristor. There could be transistor also, and 6-pulse rectifier circuit, we will use thyristor. The same, let me say, trend of discussion, the same way, circuit, operation, waveforms, and formula. Now, the same, let me say, block diagram, we have here either single phase or three phase input, and here in this block is the rectifier which contain thyristor, 1 thyristor, 2 thyristors, 4 thyristors, 6 thyristors, and so on. Then the output will be current and voltage. But because of we are using here thyristor, we expect that the power coming from the source to the supply, to the load, or from the load to the source, it's allowed. For thyristor, it's allowed. I will show you how and why. But for diode, it cannot. Diode allow only one direction flow of power. It means voltage and current should supposed to be positive, both of them. When VD, ID, both positive, PD will be positive. When one of them negative, it will be negative. This happens in the situation of when we connect, let me say here, motor, DC motor. DC motor, when it receives the energy coming from this direction or power from this direction, it works as a motor. In braking, the motor works as a DC generator. It's returning back the energy to the supply. The voltage will be negative, the power will be negative. For that, these circuits, when we have thyristor, work in quadrant 1 and quadrant 4. Quadrant 1, ID, VD both positive, so PD positive. In quadrant 3 here, VD negative, ID positive, then PD negative. Okay, so this is called rectification mode, this is called inversion mode. Now, you see here, this circuit with one diode with thyristor. We have R load, we have R load, we have inductive and back EMF. These circuits was discussed in the previous, let me say, module, and we mentioned that when, as example here, if it is diode, the pulse appear across the supply, the load, and so on. But when we have thyristor, positive voltage came here, but still not appearing across the resistance. The thyristor will be open circuit until its gate receive the pulse triggered. We call it triggered, or the delay angle came here, IG. Then the thyristor here in this point, the thyristor at alpha firing angle or triggering angle will conduct. So the voltage directly jump and appear across the load. The same thing for the current, appear across the load. So yes, here you may say there is forward voltage across the thyristor, but thyristor will not conduct because there is no firing angle came to the gate of the thyristor. This is clear? Before I go further, this is clear? Easy? واضحة? Is it clear? Great. So next, for inductive load, you remember when we discuss inductive load in the situation of diode, if this is the input, the current will increase gradually from 0 until it reach here, the voltage become negative, but still there is energy need to be released. At beta, we will have 0 current and voltage across the load. Okay, almost the same, but the difference is not at 0. We will not start at 0. You see here at 0, the thyristor is open circuit. Yes, voltage is forward, but still waiting for the pulse. When pulse came, the voltage, input voltage, which is the supply voltage, appear across the load, and the current increase again gradually because of the behavior of the inductance. And here it's negative, go to the negative, but the thyristor need to keep conducting because there is energy storage in the Inductance need to be released. It's released at this point here, and the voltage you see negative, and then switch off and back to 0. So there is delay because of the firing angle. In the situation of back EMF and inductance, what happened here, as you can see, we mentioned that there is forward voltage across the switch, the thyristor or diode, whatever it is. But the back EMF here in the opposite direction is higher. So the switch will not conduct until they intersect here. When there is diode, directly the output appear across the load. But because this is thyristor, it will not conduct. It will delay. This from here to here is the angle, firing angle need to come to the gate. When it come, then the voltage appear across the load, as you can see here. And the same thing for the current. Current will be from point of conducting, will increase gradually and release its energy until it gets 0 here and back to the same situation. So the same discussion applied there is applied here. The only difference is we start not at 0, at alpha. So that you see here the same formula we used, but rather than we start at 0, we start at alpha. You see here, this is alpha because here I call it phi 2 because we have different angles, so its name need to be changed here. Otherwise, it's alpha. Now, how we create this firing angle, or let me say delay angle, or triggering angle? How we do triggering circuits? There are different circuits available. If you back to power electronic circuit device and application by Muhammad Rashid, if you back to my book, okay, also you will find the different way of triggering, okay. But here I pick one of them, easy to explain how we create the firing angle. Have a look. The same circuit, rectifier circuit, have input, which is AC, let me say. I need to take sample of this input. So I use transformer to step down. As example, here is 230 in Oman. I step it down to 1 volt, as example. You may say, why? Because I want this point when the voltage becomes 0, in this way. Have a look. These points, I call them crossing zeros. The point when the signal go to 0. We want them because based on them, we will create our firing angle. So I got here sign. Now I enter the signal here to a sawtooth generator to tell the sawtooth generator, please generate signal in this way. Let me say this is the crossing, this is the crossing, this is the crossing. Generate signal in this way according to this crossing. I got this one, as you can see here. Now a control signal will come, which is DC signal, some DC signal, okay, enter together here into a comparator to produce the firing angle. How this happen? Have a look. I will control this comparator, let me say program it to say, you see here, this is my input, this is the sawtooth at the crossing, zeros, as you can see here, and this is the dotted line here, as you can see, is the control signal. We will program the comparator, the logic circuit here. We will control it to program it to make it work and give signal pulse when the sawtooth is higher than the control. As example, at this point here, okay, at this point, sawtooth is higher than the control signal, so pulse come, and so on here. Here, pulse come, pulse come, pulse come. You see? So we send pulse. What, so you see this control signal? When I increase it, it become here as example. Okay, then the position of the trigger or firing angle will change, and so on. If I reduce it here as example, here is the firing angle. So by increasing or decreasing the control signal, the firing angle will move its position. For that, alpha is function of V control to V sawtooth, the highest. It's a comparator between them. As I mentioned, there are different way. By the way, usually it could be having different shape, different magnitudes, different, let me say, width, the pulse. It could be like this one, it could be like this one, it could be like this one, it could be like this one. It have different shape, okay? Now let's come to my circuit. My circuit here is, as you can see here, this is the single phase and this is the 3-phase 6-pulse rectifier. I will start with single phase this session, and next session we'll continue with the 6-pulse rectifier. Have a look. We started for diode discussing the ideal circuit. It means no inductance across the supply. The same thing here. You see, rather than D1, D3, D4, D2, I call them T1, T3, T4, T2. 1 will conduct with 2. 3 will conduct with 4. 1 and 3 from the positive point, the return will be through 4 and 2 from the negative point. This is the waveform discussed in module 1. As you can see here for diode, the input signal here, positive is okay. The negative signal will be rectified to become positive again. We rectify this one here, as you can see. And the supply starts at the same time. Okay, there is no delay. This is for diode. For thyristor, no. Yes, here positive. But what happened, previous situation, thyristor 3 and 4 conducting. Okay, so they keep conduct until we receive alpha. When we receive alpha, they take over, and thyristor 4 and 3 will not conduct anymore. Here thyristor 1 and thyristor 2 will conduct the voltage and current. Okay, and it will continue until another alpha came for thyristor 3 and 4, then T3, T4 will conduct the current, and so on. So you see the difference, and this is the delay angle. For current, and if I plot input current and voltage, this is the input voltage, as you can see. The current will be delay. It's like phase shift. As you can see here, this delay is alpha, firing angle. Now, the same formula we use to drive for the voltage, output voltage, average output voltage. But the difference, the only difference, rather than we integrate from 0 to pi, as you can see here in the figure, we will integrate from alpha, here this point, alpha, into this point, pi plus alpha. So the integration change, only the limits of the integration has been changed. Otherwise, the same, let me say, integration for the input voltage, which is sine. This is maximum, this is RMS, this is sine. Integration will be minus cosine. Substitute for these two values, simplify. We have the formula here. Now I will stop a little bit here at the formula. Without cosine, just without cosine, 0.9 Vs. Oh, this is diode formula, diode circuit formula. But here I have cosine alpha for thyristor. Okay, so in diode formula we don't control anything. The output directly 0.9 Vs. But here we have controller. We have phi alpha. So if I control alpha, I control cosine alpha, then I control Vd. The output, the deliver voltage. Let's assume alpha is 0, cosine 0 is 1. Oh, thyristor, when its alpha is 0, it's behave like a diode. Okay. Now, for, as I mentioned, for ideal circuit for diode, when alpha is 0, or let me say in thyristor situation, or for diode, I call it VDO, DO for ideal. Okay, don't forget, for ideal there is no inductance on the supply. Now it was 0.9 Vs. When I want to see the difference between them, between thyristor situation and diode situation, I will subtract VDO minus VD alpha. It gives me 0.9 Vs, 1 minus Vs. It means subtracting these together. Okay. Now power also, power is just, I need to multiply here by ID. It will be 0.9 Vs ID cosine alpha. One point here to be mentioned, by the way, you see when I increase alpha, cosine alpha reduced, okay, and the voltage will reduce also. Now, the ratio normalized value of delivered voltage to ideal voltage of the diode with respect to alpha, from the previous equation, we can plot it. We will find that from alpha 0 to alpha 90, thyristor behave as a rectifier. It means power coming from the supply to the load. When it's greater than 90, it's work in inversion mode. I will show you how this happened. Let me continue with this. As you can see, I plotted this before. You can see the alpha is making a delay. It's like phase shift. We can call it phi 1. Phase shift between voltage and current. And you can see here, similar to diode, triple harmonics is still there, okay? Which is single phase, so expected we have triple harmonics. The instantaneous current, similar to the diode, square root IS1, which is the maximum, sine omega t minus alpha, while in diode there is no alpha, directly sine omega t. Here the same thing, but you can see minus omega t minus the triple, the third, the fifth, and so on. When we use this formula to find IS fundamental, we will find it 0.9 ID similar to the diode, and the same formula used for harmonic, individual harmonics is the fundamental over harmonic value, and IS is similar to ID. We assume the same input output. The circuit is lossless, no losses in the thyristor, and total harmonic distortion also found to be similar to the diode circuit, which is 48.43. Now, displacement power factor, which is cosine phi, is cosine alpha. The phase shift between current and voltage is alpha. So cosine alpha represents the displacement power factor. If I divide IS1, we have it, which is here, 0.9 ID over ID, which is IS, because IS is ID. Then we go at 0.9 cosine alpha. Power factor, we just need to multiply by the current, okay? So we have VS IS1 cosine alpha or phi, cosine phi or alpha, it's the same. This is the power. Reactive power, rather than cosine, it will be sine. These are the definition we already discussed in level 2. And apparent power is square root P square plus Q square. Now, when we have inductance, what will happen? Just let me ask you here. Do you remember what happened when we have inductance on the supply? There is a process, what we call it. Do you remember?
Commutation.
Excellent, commutation. Two thyristors will take over the conduction. It means, let's assume thyristor T1 and T2 conducting the current half part of the time. When we trigger thyristor T3 and T4, they will commutate, they switch off, they damp the operation of T1 and T2. So this commutation will affect and we lose part of the voltage. Now let me explain it here. Have a look. Now usually we have without the inductance, there is no commutation. At this point here, alpha, the voltage will the current will jump here in this way and continue as a full load current. But because of the inductance, commutation will occur, so current increases gradually. As I mentioned, it takes time. If I want to sketch it, I will sketch it in this way here. Let me zoom it, okay, here in this way. From here to here is alpha. From here to here is U. But because here is this, is the horizontal, here, from here to here is U over 2, right? So the point here in the middle here is U over 2 plus alpha. It gives me the phase shift because I want the phase shift between current and voltage. And when I sketch the voltage, have a look, I sketch the voltage. This is from here is alpha. It's supposed without inductance to jump directly and the voltage becomes this way. Because of the inductance, we have short circuit. We lose this part, the shaded part, because of commutation. Now, the same discussion applied for commutation circuit in single phase diode rectifier circuit applied here. The only difference is rather than we integrate from 0 to U, we will integrate from alpha to alpha plus U. Just this simple difference. And the same thing here is we integrate with the current and substitute from minus ID to ID. We have the same value as you remember. Okay. Now when we integrate sine, we will get minus cosine. We substitute this value. We simplify. We are here. Let's have a look at this equation. Okay. Let's assume thyristor triggered at alpha 0. At alpha 0, what we have? We have diode operation, right? We have diode operation. Okay. We have diode operation. So if this alpha is 0 here, then it will become cosine u equal. And this is 0, it will be 1 minus 2 omega LID over square root 2 Vs. Oh, it is the same equation for diode. You got it? The same previous equation we derived for the diode. The only difference here we have alpha because this is thyristor, not diode. Okay, and now Vd is not 0.9 VSID. This is the ideal for thyristor. No, it's minus the part we lose in the previous here, the shaded part. We lose it. So I need to subtract it from the total voltage. Let's apply all this discussion in this example. Okay, this summarizes the whole discussion. In the converter circuit of previous figure, okay, it's the rectifier circuit, full bridge, okay, thyristor circuit, control 1. LS is given 5%. Sometimes it's not given in inductance in Henry, it's given as a percentage of the base voltage and current. With a rated voltage VS 230, this is VRMS as you know, 60 Hz is the frequency, and rated volt ampere, this is S 5 kVA. Calculate the commutation angle U and VD with the rated input voltage power is 3 kilowatt. Alpha is given to you 30. Okay. First of all, let me find I rated because I want to convert this 5% into its real value in Henry. So 5,000, which is S, over voltage, which is 230, it gives me rated current. Z base is rated voltage 230 over rated current, which is this one. We have 10.58. So this 5% is 5% of what? Of 10.58. You got it? Okay. Now don't forget, this inductance is part of the impedance. It means omega L. Okay, omega L. So L is 0.05, which is 5%, Z base over omega to go to L. I got it. I need L. So you see here, rather than I give you directly, I give you some information, you follow them, and then you find the inductance. Easy. Next, I want to find the commutation angle. But to find the commutation angle, you remember we need ID. Okay, deliver. Now have a look. Power, he gave me a piece of information here. Power is 3 kilowatt. I know that power is VDID, which is equal to 0.9 VSID cosine alpha minus the drop, as I mentioned, multiplied by ID here. Now, this is 3 kilo, the power. LS, I already calculated. Omega 2 pi F. Alpha given 30 in the question. VS 230. What is left? ID. Here, ID square. So I rearrange the equation. It looks like it is a quadratic equation. This is ID square, and this is ID, and this is the constant. I solve it by quadratic formula. I got ID to be this value. Now, since I have ID, everything will be fine because I have the formula for VD, I have the formula for U. Okay? I can find VD and I can find U because you can see here everything given to me in the question, and the remaining I just calculated. VS I have it, alpha I have it, omega I have it, LS I calculated, ID I calculated, so I can find the delivered voltage. The same thing for U. I have alpha here and here, omega, LS, ID, VS, so you just need to do the math, substitute and simplify, and then you got the commutation angle. Don't expect commutation angle will be long, it will be short. Usually it will be short. You see at 5.9 degree, around 6 degree. Now, for this circuit, as I mentioned, we have delay, which is alpha plus U over 2. So displacement power factor will be cosine this, okay? And the input equal the output if the circuit is lossless. So VSI as displacement power factor, which is this one, equal VDID. Then I can find IS, just divide VDID by displacement power factor VS and substitute for displacement power factor by cosine alpha plus U over 2. We have this formula for fundamental current. Now until this point we are talking about rectification mode. Now let's talk about inversion mode. Inversion mode, as I mentioned, VD will be negative, which lead to negative power delivered. Okay. Now let's assume this is the input, as you can see here, VS. Let's assume the voltage, the current is conducted by thyristor T3 and T4 from previous cycle. It go to the negative, still conducting. You see alpha 1 and alpha 2, the firing angle increased. It's become greater than 90. This is 90. We are going to trigger here at this point. When we trigger at this point, the voltage will jump, okay? And because of commutation, we have here short circuit, and then switch thyristor 3 and 4 will be off, and 1 and 2 will be conduct. So start conducting, but it conduct just part of the positive voltage, and continue conducting the negative voltage and current. Okay, as you can see here, this is T1 and T2. You see before we got another trigger for 3 and 4, and we have another, and we repeat the same thing. But have a look, this part, the negative part, is higher than the positive part. So we expect VD to be negative. You see, when VD is negative, it means the minus VD multiplied by ID give me minus PD. It means the power is coming back from the load to the source. This is called inversion mode. Okay. And if we have back EMF here, we have to consider this is the situation of we are charging the battery. I mean, you know, in our laptops there is battery, in our mobile phone, in many applications, even in industry, we have battery. Then in this situation, the voltage delivered will equal to this voltage all the time. Voltage delivered equal ED. Okay, and based on this, if I plot based on this formula, it's a simple formula. If I plot VD ID for different alpha, we can see that some of them will be in rectification mode, some of them will be in inversion mode. One more point is, you remember when we discussed the operation of thyristor, we mentioned that the thyristor, just to remind you, reverse recovery time. We mentioned that the current will be in this way until it gets 0, but the voltage will be take more time. We call it TQ. This is TRR. We discussed it maybe 2-3 weeks back. You remember this? Okay. What we say it's not like the diode. Diode will be off when we finish the reverse recovery time. But for thyristor, it needs more time, TQ, because there is still some charge in the internal junction need to be recovered, then the thyristor will be off. Otherwise, if it is still there and we change back again the voltage to forward voltage, the thyristor will conduct, will not need any triggering because it's not off yet. These need to be considered in inversion mode. How? Have a look. Let's assume now the same previous waveform, but here you see thyristor 3 and 4 will trigger here at this point. As I mentioned, U will come here, commutation, still thyristor 1, 2, 3, 4, all of them conducting. Okay, at this point commutation supposed to be off. Okay, and the current taken by thyristor 3, 4 from 1 and 2. But 1 and 2 still have internal charge in the internal junction. So this gamma from here, from this point into this point, okay, supposed to be larger than TQ to say that thyristor 1 and 2 is now off. Otherwise, if we reach this point and it is not off, the voltage change become positive. Thyristor 1 and 2 back again to be conducted. Why? Because it's not off yet. It do not need a triggering angle to come. It's not off yet. So we lose control here if we don't consider this in inversion mode. Have a look. Our task is clear. We have AC, we want to convert into DC. We want to supply load. My load at the end is a production, doing something. If it is industry, we may produce food, we may produce material, we may produce whatever it is. If we lose the control, we lose everything. So we need to make sure that my circuit will be work in a right way. We control it. We know what will happen to the output. Later on, we will see how we protect the circuit from electrical or thermal, let me say, problems. So the issue is not only to connect the circuit to operate it, but we want to make sure it's work correctly. Now this is boards we have in the lab, also this one and this one. I mean, we will just work on it. For the diode, we will work also for thyristor. I think I stop here for 3-phase to continue next session with the 3-phase. Do you have any question